In the miter saw demonstration, we looked at how we improved a component's design by using an assembly analysis early in the design process. Not only did we improve the yoke by reducing its overall mass, but we also thickened critical areas to ensure that a factor of safety goal was met. But there's a bigger story to tell regarding how analysis can help optimize and improve the overall saw design, and that's the purpose of this presentation. I think it's easy to visualize that cut precision is very important to miter saw consumers. Any small errors or deviation in cut accuracy can drastically affect the overall outcome of a woodworking project. So, for this miter saw, a manufacturer may have a design goal to keep saw deflection below 0.02 of an inch, or 0.05 of a millimeter. The question may be asked, how would you validate that designs meet performance expectations? Many companies spend considerable amounts of time and money in creating physical prototypes and putting them through rigorous test cycles. Cosmos is a better alternative. It not only helps validate that designs meet expectations, but also yields a tremendous amount of information that is hard to visualize in physical prototypes. The best part is it's extremely easy to use. If you know the operating conditions of the product, you can apply them to the model. Here, we know that people will push down on the handle of the saw with about 5 pounds of force, or 22.24 newtons. We can easily pick the surfaces of the handle and apply those forces in a downward direction. Likewise, we know that the saw will sit on a workbench, so we can easily choose the bottom surfaces and tell Cosmos to restrain them in place. It's an extremely easy process, and there's a lot of value to the fact that Cosmos uses the same user interface as SolidWorks. You can pan, zoom, and rotate the model in the same way, and Cosmos recognizes all the SolidWorks geometry, so you can use surface edges and vertices to help define the operating conditions. The next step we have to do is define what we call contact sets. Contact sets simply describe how components will transfer forces to each other. Even though the saw model is fairly complex, we only have to worry about a few key interfaces, where the head assembly meets the yoke pin meets the yoke, the linear slide interfaces with the pedestal, and the pedestal interfaces with the base. We have a few examples to show you that illustrate how simple these contacts are to define. Again, leveraging the consistent interface of SolidWorks adds value. If I have an exploded configuration defined in SolidWorks, I can use it to help show the parts in a nicely spread out manner. I can use that view to help pick surfaces that interface with each other. Here we are choosing the outer surfaces of the pin and the inner surfaces of the yoke. We are instructing Cosmos that these components will push on each other, yet their volumes will never intersect. We can show you a similar example of how we created the contact between the pedestal and the base. Again, you simply select the faces and tell Cosmos that these surfaces will push on each other without penetration. Once these contacts are defined, we're ready to let Cosmos mesh and run the analysis. And meshing is done automatically. If you're familiar with the concepts, I think you'll be impressed with the complexity that's found in the miter saw mesh. You can see from this slide that Cosmos has meshed the entire assembly, a task which traditionally would be considered very challenging due to large geometry variations. We have very thin saw blades, we have thin rails for the linear slide, yet we have thick castings. So a lot of different geometry types in this model, and Cosmos handled it without issue. Also, if you're familiar with the statistics of meshing, you'll see it's a very large mesh, and again, no problem at all for Cosmos. Now once Cosmos is done meshing and solving this study, we can easily visualize the results and start getting insight on how to improve the design. An easy way to interpret the results is to animate the stress plot. We can determine which components undergo the most stress and also determine how forces are propagated throughout the assembly. The 3D interface allows us to interrogate the model from any angle. And here we see that the saw blades do see a lot of stress, but the linear slides and pedestal also have considerable amounts of stress and contribute to the deflection. So right away, Cosmos has given us great insight into our design's performance. However, the miter saw problem is a bit more complex. The saw has numerous operational positions, and it's important for us to determine which positions yield the greatest deflections and cut. The good news is that in Cosmos we're able to easily repeat studies on different positional models. We can rerun the analysis and animate and compare all the results. Here we found that the cut accuracy only violated our design goal when the saw was rotated at 45 degrees and the linear rods were fully extended. So we want to make some design changes so that this extreme position of the saw will still meet our design criteria. The tight integration with SolidWorks again comes into play. We can easily add some stiffening ribs to the back of the pedestal and see its effect on the overall deflection. You can see from the graph that only a small change was needed to meet our design goals, and a simple rib pattern did the trick. We successfully reduced the saw's deflection by 10%, and we are confident that the saw will maintain its accuracy throughout its full range of motion. Stress and deflection analysis are common tools to help you build better products, but Cosmos has so many more capabilities which can help validate our saw design. We use the exact same setup to run a frequency analysis to determine whether the saw would experience vibrational issues. As you know, the saw has a motor and a blade that spins at a specific speed. We can use Cosmos to determine whether the speed will excite the natural frequencies of the model. Cosmos will identify the frequency modes and even allow the users to visualize the vibrational motion. We have tool sets that look at mass participation during vibrations, so we can see how each modal frequency affects the individual components. The good news here is that there's enough variation between our saw's natural frequency and the speed of the motor and blade that excessive vibration should not be an issue. We also can conduct fatigue studies on the saw. We wish to validate that our saw can withstand rigorous cycles of use. Here we're able to simulate the saw conducting 100,000 cuts. Our design passes without issue, suggesting that normal wear and abuse will be the primary factors that will affect saw life. So in summary, Cosmos provided extremely valuable insight into our saw design. Early in the design process, we were able to define goals, check the product's overall performance to these goals, and refine our design accordingly. The result is that we have a design that will operate at superior levels of accuracy, comfort, and longevity. The entire validation process did not take long at all, yet saved tremendous costs associated with prototype testing. Believe it or not, there's even more that Cosmos can do, and this is a great slide. It shows you the entire capabilities of the CosmosWork family of products. Everything from pressure vessel analysis to drop testing, nonlinear, random vibrations. Of course, we have Cosmos FlowWorks that does flow simulation, and even electromagnetic studies with our Cosmos EMS product. All these packages are priced very affordably, yet provide tremendous value, design insight that you can use early on in your design process to ultimately make better products. Thank you.